Um, Now, I didn't even get the homework, I don't think posted, did it? Posted. There is some up there now, you can see it, but I know it was before then. Don't worry about that right now. What it really boils down to is op-amp problems, operational amplifier problems. Here's what we're gonna do. I'd like to take care of the operational amplifier problems, and any questions about realization using that method I showed you, where you divide top and bottom of an actual transfer function by the highest power of S, and then realize it using negative feedback. Y'all remember that class? Those are things, I'll give you some more problems on that, and you'll be responsible for it. However, the op-amps is the thing I'm really worried about. I'm not worried about, I'm not concerned that much about negative feedback realizations yet. Now, did you, since there are no problems, I hate to do it. Operational amplifiers, you went over, there were two basic laws, right? No current in to the actual differential terminals and no voltage across them, right? I want to do one more problem with operational amplifiers. I put some problems up there. This one, what I'm trying to do is related to the actual flow. You get most of this, I think, in your, but do you have analog electronics yet, or not? No. All right, that's where you're going to get a lot of this. I'll just show you a couple of problems that I want to take you through. I'll let you do a few of them. This is going to be 4.31. What they have is they have a resistor R here, and a capacitor here. And then they have this going into the negative terminal of the op-amp, this the positive terminal, and they have a voltage here, plus to minus, and this is called V1. This is grounded. And there's a resistor, this is R1. And this resistor will be R2. And they want this voltage. We'll call this V out. Now, let me show you a few things about this. We're going to do this in the S domain, not the time domain. A ground means it's 0 volts, right? Just so nobody misunderstands that, just take a line and put 0 volts there. So everybody knows every single voltage is referenced to 0 volts or ground. Now, when you have that, the next thing I'm going to say is that if we just do the basic things I told you to get the output voltage, we should have no trouble. Now, think about what the basic things were. What's the voltage difference between these two terminals, class?
0.
Therefore, this voltage would be
V1.
V1, right? The voltage difference 0. V1 is here, V1 is there. Do you see it?
Yeah.
Now, if V1 is there, how much current flows this way? I'm going to just call this I1.
It's going to be V1 divided by R1 over plus C.
Well, what we have to do, that's not 6, that's C. This has an impedance of 1 over CS. Do you follow me, class? We're in the Laplace domain, so the impedance of the capacitor would be 1 over CS. Are you with me? Therefore, this current I1 here, and I'll put it over here, would be equal to simply V1 over R plus R1 over C1S, or really CS. There is no other capacitor. Do you all agree with me? All right. Now, if that's the case, go back here. It's purely deductive reasoning. There's nothing tricky about this. If all this current I1 is coming this way, how much current leaves the negative terminal? None, right? No current in or out of the differential current, the differential inputs, right? That's critical. Do y'all follow me? I know you're saying, how can that be? It's done by the electronics. It's an active thing that has maybe 1,000 to 10,000 transistors creating this effect, all right? We're just showing you the block diagram. So if no current comes out of here, where does all this current come from? This way, right? That's I1. Do you agree with me? Everybody see this? Please make sure you do. Now ask the next logical question. How do I get my V out at that point? What do I do next? Anyone? Anyone? If I got I1, you all agree I got I1? So what's the voltage across R2?
Take I2 times R2.
I'm going to put a plus to minus, and I'll just call that VR2, and VR2 would be what? I1, right? Times R2, or since I1 is V1 over R1 plus 1 over CS here times R2. That would be VR2 as I show the polarities. Does everybody agree with this? When you start seeing this, you'll realize how easy it is. This is an ideal operational amplifier. Admittedly, in real ones, there are slight offset biases you have to deal with, but for the most part, this gets you almost 99.9% of where you need to be. Just doing it this way. Now, once I have that, what's my output voltage? Here's where you need to be careful. How do you always get, this is how when I used to teach circuits, I said, whenever you want the voltage between 2 points, you start at the negative terminal with respect to the voltage you want. I start here. I go around, this is a voltage increase, right? An increase of V1. Do y'all see that here, class? Increase of V1, and this is a voltage, what?
Increase.
Increase of VR2, correct, class? Do y'all see that? So I could say V out is going to be equal to V1 plus VR2, or it's V1 plus V1 times R2 over R1 plus 1 over CS. And at this point, it doesn't matter how far you go with this one. You can take this V1 and put 1 plus R2 over R1 plus 1 over CS. And if you want to, you can get a common denominator, and you can keep on getting into any form you want. But do you see the essence of what I've done here, class? Yes, sir.
So, you said that there's no voltage where that thing is right there. I don't know what it's called, but you said there's no voltage.
There's no voltage difference between here and here.
Okay.
That means the voltage here must be the same as the voltage here.
Gotcha. Okay.
That's
So-
all it means. This
Okay.
voltage, V, in the book, it will have V sub plus equals V sub minus. All right?
Okay.
1 volt here, 1 volt here, period.
So when it goes through the V1 and then it goes into that, it's not a V1 minus V1 thing?
Well, if you start here at the negative terminal, if you remember how to do this in circuit analysis, you're coming around here, that's 0 potential difference.
Right.
This goes from a minus to a plus, it's an increase.
Right.
It's plus V1.
And then when
Then it comes here, and from here to here, you'll notice it's minus to plus as well, right?
Mhm.
So it's a voltage increase as well. Are you with me?
Yeah, what I was saying was just, it's going from the minus to the plus on the V1. Then it goes inside that thing from plus to minus.
What is going? I'm trying to figure out what you're
Like, when we're following the
This?
thing, right.
All right, the way I'm going around is from here to here. That's an
So
increase
you
in
don't- And then you don't go inside of that?
Well, because this is the same voltage as here, I can just jump over to here, right?
Okay.
There is no voltage change between those terminals, so I don't even, there's not, you don't have to take a delta either. Are you with me, class? You'll notice one thing about this, it's not inverting, is it? Now, that's why they call this the inverting terminal and this the non-inverting. Whenever you put a voltage, no matter what the network is, where you're feeding the negative terminal primarily, like either through a resistor or whatever, then you'll get an output that's inverted. When it comes to the positive terminal, it won't be. I mean, there are some, that's generally true, there are some things that will make it not true if you really work at it, but that's basically it. Are you with me, class? Y'all see it? Gotta do another one. Did you have anything with operational amplifiers in your laboratories yet?
No.
None? Okay. A lot of times you do. Even in physics labs, I think they have operational amplifiers used, don't they? Can you,
No.
not,
In 2300, not,
what's that,
not physics 1 or 2.
2300?
Yeah, later on,
Oh,
but not 1 or 2.
okay. Well, it's important. And the next circuit I want to do I'm going to put this one up here. This is a little more challenging, but I want to see how everybody thinks about it. This is 4.32. Here, we have a voltage. This is VS, the source voltage. Comes through R1. Then, through R2. Then it goes into the positive terminal of the operational amplifier. Then there's a capacitor here to ground, and that's C2. This is the output voltage. And then there's a C1 here. And that goes to the out. Got C1. Let me draw that from there. I have C1 there. This goes right to the output here, and it also ties to the negative terminal there. This is a little trickier. And I got R2, R1, C1, C2, and VS. Now, when you're looking at this problem right here, okay? Your instincts say start at this end, right? There's where VS is. Well, now you look over here and you take a look at what's going on. There's no clear to ground path where you could just take a certain impedance and divide it into VS to get the current. Does everybody see that? So the minute you see something like that, then you work from the other end, or the output voltage. Remember, it's always a relationship between input, output we want. What we really want is this, the transfer function of this circuit. H of S, the transfer function, is the relationship of V out of S over V source of S. It's always a ratio of the output to input voltage. Are you, now please get familiar with that. That's called a transfer function. Back in the day when you had circuits, Dr. Irwin's class probably called it voltage division in primary, the most basic way, but it's always a ratio of output to input. Transfer function. Now, watch carefully. Take a look at what we know. We don't know V out yet, but V out's there. Do you agree with that? So if that's V out, you see how V out is at this negative terminal? Everybody? So if you got a red mark or something, you can do it this way. Just put V out there. Now, if V out is there, what's the voltage at the positive terminal? V out as well. So if V out's there, what's the current through this capacitor? Remember, the impedance of this is 1 over C2S, right? What's that current right there? Everybody hear that? I'm going to go ahead and just label this IC2 for now. And I'll put IC2 here. It's simply going to be V out over, or really V out divided by 1 over C2S, so it's really what? It's S times C2 times V out. Do you agree with that? Because it's 1 over SC, right? Please take a look at that. I don't want to run through anything. Y'all with me on this? Jeff, can you see? Hospital. All right, so that's IC2. How much of IC2 comes out of the positive terminal of the op-amp?
0.
None. Please make sure you state that over and over. There's no current that flows out of that positive terminal. Understand? Because current is flowing, where must it come from? R2. Has to flow through here, right? So that this whole thing is going to be IC2. Correct, class? Do you all see that? Give me a show of hands if you do. With me? What don't you see? If the current is flowing this way, and we know IC2, if you give me that, then the only place that current can come from is this direction, because effectively that's an open circuit. Make sure you see that. Understand, everybody? Now, if that current's coming there, what is the voltage between here and here? Just do it logically. it would be the current, right? The current is what? It's SC2 V naught, right? That would be the current. Wouldn't it be that times R2 plus 1 over C2S class? So let me label this right here. I'll call this V2 for lack of a better term. And I would say V2 here would be equal to all that current right there times R2 plus 1 over C2S. So it's really IC2 times R2 plus 1 over C2S. And since that is IC2, it's S times C2 V out times R2 plus 1 over C2S. I'm just writing this down. I'm putting it in here so I'm letting you think about what I'm doing and why I'm doing it. Things, bells should be going off now. Now, if that's the case, you can all see that the last term here, the C2S, is canceled. So then I get what? I get V naught, right? And then it's going to be, I have S, right? Then C2 times R2. So S, C2, R2, right? Plus what? 1. Do you all agree with that? Plus? Please take a careful look. Make sure I don't make a mistake. Do you agree? All right. Now I've got this voltage. What's my next thing? Yeah, I could go that way, but I have this voltage and I have this voltage, right? Can't I get this current? Can't I get IR1 here? Do you agree with that? Everybody? All right, now when I look at that, what happens? I can put this down. This is going to be V2. And when I put down IR1, I see that's equal to what? Vs minus V2, not that, V2, over R1. Do you agree with me? Agreed? I'm going to go ahead and fill in for that. Try to get this. So this becomes, here, IR1 is equal to Vs minus V2, which is V naught, times 1 plus S R2 C2 divided by R1. Agreed? Right? Now that's IR1 flowing here. This is IC2 right here. You'll notice they both are in terms of V naught and Vs, right? What do you know about that? That this current has to equal, depends which way you want to take it. If I take the current going this way, call that IC1. I know that IR1 has to be equal to IC1 plus IC2, correct? Agreed? Y'all see what I'm doing? It's not. All right, so now we have V2 here. What is IC1? Let me put it over here. Just take a look at that. Anyone? IC1, the current flowing this way. What do you always do? Take the voltage at the point the current enters, right? Minus the voltage on the other side of the impedance divided by the impedance, correct? Right? So we have V2 minus what? Class? What's on the other side of that cap? Come on.
V out.
V out, thank you. Divided by?
1 over.
Times and divided by 1 over C1S, right? Because this impedance is really 1. 1 over SC1 right there, isn't it, class? All right, so what I'm going to say is it would be divided by that impedance, or really times SC1. Do you agree with me, everyone? Please make sure I'm not doing something wrong. Are you with me? In the back there? All right, now what am I going to do? I've got IC1, I've got IC2, and I've got IR1, right? How did we, well, we said that current goes up. So what's the final equation? We have IR1, right? That's going that way into this junction. What's it equal to? IC1, right? Plus IC2. Do you all agree with me? I want to make sure you see why I'm going to write what I'm writing. Are you with me on that? Now fill it in terms of the voltages, V out and Vs. What is IR1 right there? Or I mean, yeah. IR1 is over there, right? And that's, help me on this one, IR1 would be equal to Vs minus, right? Vs minus V out times 1 plus S R2C2. Do you agree with that? Divided by R1. That's on that side. And it's equal to IC2 plus IC1. Oh boy. Let me write it down here. Vs minus V out over 1 plus S R2C2 here over R1 equal to, now it's equal to IC1, which is here, which is V2, pardon me, V2, and V2 is, where is V2? I wrote it somewhere. Over there, right? See it? Class?
Yes.
V2, so I'm going to put V2 here, which is V naught. I got V naught here, so I'm going to factor out the V naught. And I get 1 plus S C2R2, right? And then it's going to be minus 1. That's IC1 times, that's V naught times that times S times C1. Yeah, that's IC1 here, right? And IC2 is what? Isn't that it? Plus S C2 V naught. Now, just take a look at this for a second. I'll clean this up. You have to see, now isn't everything in terms of V out and Vs? It's a bookkeeping kind of problem, isn't it? Just keeping the books. It gets a little awkward. Now, everything's in terms of V out and Vs, correct? So if we get the ratio of V out to Vs, don't we have the transfer function H of S class? You all follow me what I'm saying? If you take the output over the input voltage, that's what we want, right? So now we simply divide everything by Vs. Follow me? Are you listening? Right? If we divide by Vs, what do we get? That becomes 1. This becomes V out over Vs, right? We're dividing by Vs. This becomes V out over Vs here. You don't have to do it this way. And this becomes V out over Vs as well. Most of you can see we can combine all those things, can't we, class? Right? Are you with me so far on this stuff? Now, what I'm going to do at this point, I'm going to say here, if I wanted to, I'd multiply by R1 on this side. And then, do y'all feel you can solve for V out over Vs yourself? And this one from here on? Here it is, V out over Vs, V out over Vs, V out over Vs. You would take all the V out over Vs terms to that side, everything that's constant or functions of R, C, or S to the other side, and just divide by the coefficient of V out over Vs. How many see that there? Can you do it? You're very quiet right now.
Can you show it to us just in
Yeah, I'll do it right here. You realize it's basically keeping the books. This problem is not a tough problem in the sense of, it's a really intricate math or anything like that. You just have to organize and keep the books right. Now, what I'm going to do here, and you'll have to keep me straight on this one. For this one, I look at this term right here. I'm going to take it to the other side, all right? I have V out over Vs for the negative side times this. It's going to the other side. That means it comes over here, and it's going to be plus V out over Vs here. And it's going to be 1 plus S R1C, R2C2. So So now we can erase this. Y'all agree? I'll put a 1 here. With me so far? Let's see what we can get rid of. Now, if you look at this, just look at the coefficients of V out over Vs, and I'll put it over here. When I take a look at V out over Vs, which is my transfer function, right here, I have R1 times this, right? But 1 minus 1 is 0, right? So I can get rid of that. Y'all agree with that? So really, I have R1, R2, C2S as the coefficient there. So I have S, and I have C2, R1, R2. I've just taken care of this entire I've taken care of this right here. Haven't I, class? Right? But there's also an SC1 here, right? So that makes this a squared, and I better put this on here, so it's now S squared times C1, C2, R1, R2. That's this entire term here. It's the coefficient of V out over Vs. Do you agree with that? Keep going on this one. You see the coefficient of V out over Vs here is SC2R1. That's this. With me? Last part, what do I have here? I have 1 plus S R2 C2, right? Now, I'm going to put the 1 out here. But you'll notice that's S times that. So what I'm going to do, there's an S here. I'm just going to add that plus R2 C2 here. Are you with me? How many see this? You realize this is a quadratic, right? R2, C2, I mean, that's basically quadratic. What we really do in a second, we would divide everything by C1, C2, R1, R2, so the coefficient of this would be 1. But you can see the only thing I have to do is take this right here, this entire chunk, and divide it into 1 now. Don't I, class? And then, in fact, I would get the transfer function. How many see that? That's what the book has as an answer. They may give you values for R1, R2, C1, C2, and ask you for the actual impulse, the H of t or something like that. But you see, this is the way it's done. Now, it's really circuit analysis. That's all we've done. We've applied circuit analysis and to the actual fact that the impedance of a capacitor is 1 over Cs, and if there was an inductor, it would be SL, and there are no initial conditions. Got it? Now, that kind of a problem you'll see. You'll get problems like this. I want to make sure I did those, at least 2 of those problems. There's one more problem for homework that's up there. These 2 were there, and we did them. All right? Now, the next thing we're going to do, we're basically done with Laplace transforms. With Laplace transforms, I'm just going to mention one last thing with Laplace transforms. And this is something that I've mentioned before, I believe. I want to just say this. This has a lot to do with stability. Do you remember what I said? If you had a function, and you had some function, transfer function, h of s, equaled some numerator, n of s, divided by some denominator, d of s. I said one thing. For stability, the poles had to be in what? The left-hand plane, correct? Strict left-hand plane. I'm just going to mention this one more time. When we talk about the S-plane, this is always the real part of S, and this is the imaginary part, or the J part. Now, a pole here or here, X's are poles, indicates that it would not be stable. It would just exponentially grow the output, or maybe even faster than that. Are you with me? When there's poles that occur on the J-axis here, that's marginally stable. Let me give you an example. Suppose I have an LC circuit in parallel. Now, you can do the math on this, but if I look at the impedance on this, and write an equation for the input impedance, I'll find out that when the actual, well, let me take that back. Let me do it this way. If I have a series LLC circuit, you'll find the impedance at resonance is 0, which means the current would go to infinity. And in a circuit like that, it would be unstable unless something limited the current. Are you familiar with LC circuits, class? What happens at resonance, the impedance of the inductor is exactly the same in magnitude, but opposite sign as the impedance in the, the capacitor's impedance is the same as the inductor's impedance with the opposite sign, so they cancel. Now, if they're in parallel, and you're driving an LC circuit at resonance, you have an infinite input impedance. It looks like an open circuit. But if they're in series, you have 0, which means any voltage that's finite fed to that thing would cause it to fail catastrophically. All right, it would burn up, theoretically. Follow me? But there was always finite resistance in real circuits that would limit that. It still is probably going to burn out. However, when they're in parallel, even though the poles on that one are on the J axis, right, it will not destroy itself because, in fact, it looks like an infinite piece. Are you with me on this? So even though the poles could be the same for these networks, and I'm not going to spend much time on this comes later, it depends on the configuration, whether or not they're destructive. It's going to be completely, if it's stable or not. However, any pole in any part of the right-hand plane, the right-hand plane is everything to the right of the J-axis. They will be unstable, and whatever system you've got is going to go into failure. Failure means so many different things. I talked about the swept board when planes would rip apart, and anything will cease to work as it was meant to if it goes into a failure mode. Most are not self-healing, some are. There are some situations that they heal themselves, most are not. All right, that's the only thing, last thing I will just want to mention one more time before we go to our next step. A lot of this is it's going to all come back at you and come together a little bit later in something called the Z transform. But now, what we're going to look at is Fourier series analysis. What we've done so far, we've looked at a lot of different ways to analyze signals, or we've analyzed systems using S, and the Laplace transform, if there's one thing you pick out about that, it allows you to build circuits that basically realize function. Following on that? That was the one real benefit. You could both realize or synthesize and analyze circuits. It's important. Now this is strictly for analysis. You don't use this for synthesis, but it's a very powerful technique, and it's when you have a periodic signal. So here, this is Fourier series analysis. Now, this is probably one where if you get this from the math department, they'll spend a whole lot of time doing the sine and cosine series. I don't do that. I'm an engineer. I know what we use. We don't use it. We use the exponential Fourier series, and I'll explain. And there's a reason for it. And the reason I'm using it, have you all noticed that our transforms, the Laplace transforms, it was e to the minus st, right? Times weighted by the function x of t and integrated. Well, you see, you could take that e to the minus st and represent it as also, if you made s equal to sigma plus j omega, a cosine plus a sine. But I don't want to mess with that. I want to make it as simple as possible. So now I'm going to say, first, if you have a periodic signal, so this is only for periodic signals. What does a periodic signal mean to you? Something that repeats itself in a timely fashion, and it looks the same all the time. The best examples are like voltage on the actual 117 volt RMS line here, right? Periodic, a square wave that repeats itself over and over again. They have an infinite amount of energy, theoretically, but they have finite power. There's a finite amount of power, infinite energy. Yeah? So if we talk about a signal, and I'm just going to draw one here. Suppose we had a signal like this. And this is in the time domain. All right? The peak of this is A. Let's call this signal x of t. Doesn't matter what you call it. I'm going to say this is tau, and this is t. Now, for the record, t is called a period. It's it's the time it takes for the thing to repeat itself. And you'll notice that's a period, that's a period. Follow me on this, you're familiar with this, aren't you, class? How many of you have seen this before, period? You surely should have. The next is something called the fundamental frequency, F naught. F naught is simply 1 over the period. That's called the fundamental frequency. That frequency is in hertz, or cycles per second. Normally, well, a lot of times you're going to have omega naught, and that's 2 pi f naught. That's the radian frequency. It's still the same thing, only in radians per second rather than cycles per second. Are you with me, class? Now, once you have that, I'm just going to put this down. I'll prove this in a second. I can represent any periodic function, x of t, as an infinite series. I'm not going to do the sine and cosine series. I'm going to say n equals minus infinity to infinity of c of n e to the j n omega naught t. Here, omega naught is the fundamental frequency in radians per second. N is a strict integer, 1, 2, 3, 4, 5, and so forth. It cannot be 1.3. It's an integer. The summation goes from minus infinity to plus infinity. But I'm going to say any periodic signal can be represented like this. Now I'm going to show you the proof for this. It's a little trick, and don't worry about it. I'm just going to show you so you get it. Does anybody have Fourier series in here? You have? Well, I know he has. But, all right. So what I'm going to do is this. You don't have to write this down if you want to. Just enjoy it. It's in the book. I'm going to multiply both sides of this equation by e to the minus j m omega naught t. So now I take x of t, e to the minus j m, not n, omega naught t. And that would be equal to, now with this summation, since I'm multiplying both sides by that, I have c of n, e to the, and then here it's going to be j, and it would be n minus m omega naught t. Do you all see that, class? If you multiply both sides by e to the minus j m omega naught t, you're going to add the exponents on the other one, right? Agreed with that? Now what I'm going to do is integrate. I'm going to integrate both sides. I'm going to just go over a period. I can go from any point to any point plus a period. That's going to be dt. So I'm going to take this and integrate it from 0 to t, dt. If you want to write it down, you can. It's not necessary. It's in your book, and this is a very, very classic. It's one of the more well-known things that you get presented with in signals and systems. You'll see this over and over again. I do this in my radar course. I do it in my EMC course. I think I do it in my EMAG courses. And you're going to see it all over the place. You've probably seen this before, something like this. Now, here's the deal. Look at this for a second, and look at this range from 0 to t. Omega naught is 2 pi over t, is it not? Don't write this down, just watch, and I'll explain something. So if this is 2 pi over t, and these are integer values, and I'm integrating from 0 to t, I'm integrating over a period, am I not? Or 2 periods, or 3 periods, right? Are you with me in that, class? And we know what? If we have, and just following on this, if I have e to the j theta, that's equal to cosine theta plus j sine theta, correct? Isn't that right? What's that called, by the way? Whose proof? Euler's identity, right? 1 of 3. Y'all remember that? Now, if you take this and you integrate this, d theta, from 0 over a period is 2 pi radian, d theta, from 0 to 2 pi. Well, what is the integral of a cosine waveform over a period? Anyone?
0.
It's 0. Well, it's actually, you're right, it's minus
Sorry.
sign, but you would evaluate
The
it.
limit's at 0.
It will be 0. The area above is the same as the area below. Follow me? What is the integral of a sine from 0 to 2 pi?
0.
0.
0, any cosinusoidal function, or sinusoidal function will always be 0. which means anytime n minus m is finite, 1, 2, minus 1, minus 5, you'll get 0 there, follow me? But there's one time when you won't. What happens if m equals n? What do we have? If m equals n, what happens here?
E to 0.
Then I get 1, don't I? Follow me? So if m equals n, and you'll notice now that sum goes away, doesn't it? Now we have only one term, where m equals n. And in that case, if I have c of n, right, and I have 1 from 0 to t dt, don't I have just c of n times t? Right? Because if you integrate dt, you get 1, right? I mean, you get t, from 0 to capital T. Evaluate. Are you with me, class? How many see this? This is a very interesting. So now I can say that side is c of n of t, and this side is something that I need to integrate. But now you can make that anything. The n went away, didn't it? Follow me? N just had to be equal to m. Well, now you can make this an n if you like. And you can say now the value of c of n, the actual value, because n has to be equal to m, is equal to 1 over t, the integral from 0 to t, of x of t, e to the minus j n omega naught t dt. And this is how you get the coefficient c of n. And I got some more tricks for you that are really nice. It'll save you an immense amount of integration by parts pain. Now you all see, the reason I did all this is to get this, so write that down. That's the c of n that goes here. And believe me, it works. Okay? You're asking yourself, why are we doing this? Which is a good question. Well, eventually I'm going to turn this thing into a series that is just a magnitude of some coefficient c of n and a cosine of n omega naught t plus a phase angle. Now the reason I'm going to do that, because that is the exact way we could represent a phasor, magnitude and angle, if it's a cosine varying waveform. You remember before, if you had 10 cosine of 377t plus 30 degrees, that could be represented as 10 at 30 degrees, and you would just use the frequency 377 to calculate the impedances on the inductor and capacitors in your system, and you could solve the network, right? That's why we're doing this. Just so you know, it's not all for driving you nuts. That's the real reason, the motive. Now, if we have this here, I'm going to show you now, we could do a simple one, and we will. This way, we're going to brute force it. But I'm going to show you a very nice trick in a second. So suppose, I was going to get back to that waveform, I don't think I'm going to have time. Suppose we want to calculate the Fourier series coefficient C of n for this waveform. Just write this down. This is an easy one. This is t, and this is my x of t, and there's other functions. It's a square wave. Just repeats itself forever. Make this height a. I on purpose chose these values. Now, the first thing you have to do is find the period t. I got one more thing to tell you. What's the period? Careful, look.
It's 2.
2, right? It repeats itself over, it takes 2 seconds. Make sure you see that. 2 seconds. This is seconds, by the way. It's seconds. So the period is 2. It means omega naught is 2 pi. Let me do it F naught first. F naught is 1 over t, or 1/2 hertz, right? And omega naught is 2 pi times F naught, or it's simply pi, radians per second. Do you agree with me? Now this is the one thing I didn't say. This is the way you get C of n for all values except n equals 0. This is important. You use that to get C of n for all values except n equals 0. I'm going to add one other thing too, and I don't want to try to confuse you. It doesn't have to be from 0 to t. It has to be from some point to some point plus a period. So to give yourself a little more leeway, you don't have to put 0 there. You can put some value epsilon. And epsilon can be anything at all. It can be any value at all, as long as the value up here is epsilon plus t. Exactly one period down the road. Got me? Now, with that in mind, you never use this to calculate the value of C0. Here's, well, you do, but when you calculate C0, what happens? E to the minus j n omega naught t is 1, isn't it? Right? Follow me? So the way you always calculate, don't use this formula, just put C0 is equal to 1 over t, the integral of x of t, dt, and it can go from epsilon to epsilon plus t. What would you call that in common language? If you integrate a function and then divide it by the range over which it exists, there's a term you engineers know, all of us know. It's the average value. That's the average value of the function. Follow me on this, class? Y'all see that? That's all it is the average value. Now look here. Without even doing any heavy math, what is C0 here? Just by inspection. It's really the area, right? Think about the area. Well, the area would be what? 1 times A, right? Divided by the period, 2, or A over 2. How many see that? That's all it is. It's just A over 2. It's that easy, too. So that's C0. Now we're going to go get C of n for this, all right? So for C of n on this one, what is it going to be? And I'll do it right here. C of n would be 1 over the period. What's the period? 2. Integral. We can go right from, we'll start at 0, but where do we stop? Here's a trick. Take a look at this function. It has a value that's non-zero all the way out to, and then it's 0. What's the integral of 0 over any interval?
0.
0. So you just go from 0 to 1. What's the value? A times e to the minus j n omega naught t dt. I'm going to leave it as omega naught here. What happens to that when you integrate it? Well, I try to be careful about this. When I do this, I'll take the a over 2 out in front. When I integrate e to the minus j n omega naught t, I get 1 over minus j n omega naught, right? And then it's going to be times e to the minus j n omega naught t evaluated from 0 to 1. Correct, class? Do you agree with that? I just did the integration. Correct? Now I'm going to tell you this. You can do this a million ways. When I have this right here, I could take 1 over minus j to the top is what? What's 1 over j? Anyone? Minus j, isn't it?
Yeah.
Do y'all know this, class? J, 1 over j is minus j, right? So if I do that, I can just, it's up to you how you want to do it, but I can just make this j here because it was minus j, right? Now when I'm evaluating this, what do I get? Take it over here. I have c of n equals, right? I have a over 2, and then I have j over n omega naught, and then I have e to the minus j, and omega naught's what? Omega naught was, I wrote it down, wasn't it pi, class? Right?
Yes.
So this would be e to the minus j n omega naught times 1, or simply times pi here, minus 1, e to the 0. Are you with me? Now if you look at this for a second, I am on it. Just looking at this for a second, I want to show you something. Evaluate this when n is 1. Do it in your head. What is e to the minus j pi? What is e to the j pi? At what angle? 180 degrees, right? 100. What's 1 at an angle 180 degrees? Negative 1. Isn't it, class? So it's minus 1 is minus 2, is it not? So n odd, it'll be for every odd value. This will be minus 2 divided by 2 is just minus 1. Minus 1 a times j, and it'll be divided by n omega naught, will be for all values of n odd. I don't have time to go on and on about this. Now what about n even? Think about this. Suppose n is 2. What is e to the j 2 pi?
That's 0 or 1.
1, isn't it? Right?
Yeah.
Anytime you have e to the j 2 pi times n, you're always 1. It's always going to be 1, right? Because the hands of the clock wrap back around. So it's 1 here, minus 1 is
0.
So it's 0 for n even. Follow me? I'll get more into this next time. All right, thank you for being attentive to give me an extra minute or so. Sorry about the game. I hate the outcome as much as I hate it. I have to live with somebody. not with, I mean with rounded.